So I want to begin with a review of Metropolis algorithm as it's applied to Bayes' theorem. So we start off with initialization. So we specify a current value of theta. And then we calculate this thing we're going to refer to as the probability of the current value of theta. And we're going to define it by taking the likelihood of the data given that value of theta multiplied by the prior probability of theta. And if we come down and look at Bayes' theorem, essentially what we're doing is we're going to get rid of the denominator, replace it with a proportionality sign, and then this thing here is what we're generating. Then we're going to come up with a proposed value of theta, and theta proposed is going to be equal to theta current plus some delta theta, where delta theta is going to arise as a random draw from a normal distribution standard deviation sigma. We'll talk about this more next week. We're going to calculate the probability of proposed, and the probability of proposed is going to be as shown here, and once again it's just going to be this numerator. So once we've got probability of proposed, we're going to divide that by probability of current. We're going to look at that ratio, and if the ratio is greater than 1, then we're going to accept the proposed value of theta. It becomes the new value of the current value of theta. We tally it and return. Otherwise, if the ratio is less than 1, then we compare that ratio to a randomly generated number from a uniform distribution that goes from 0 to 1. If the ratio is greater than that number, we accept the proposed value of theta and go in this direction. If the ratio is less than 1, then we retain the current value of theta, tally it, and the process repeats it. And so on E-class, there's the program MCMC by hand that implements this for the handedness experiment. And what we get is a histogram shown here in these dark bars that corresponds pretty much exactly to the dashed line, which was obtained by conjugate priors. So in terms of what we need to make all this thing work, there's a number of things that need to be provided to the computer. First is we have to have the initial value. So we had this initialization up here. Second thing we need to do is give it the data, which is y successes in n trials. Thirdly, we needed to have the likelihood, and we specified the likelihood as the binomial. Needed to specify the prior, and based on my family situation, I specified the prior as a beta 4-2. And finally, we had to get this delta theta that we'll talk about next week, which comes from a normal distribution, mean 0 standard deviation sigma. So if we do all that, we can use this Metropolis algorithm to obtain the posterior distribution. Now what I want to do is talk about the math behind the Metropolis algorithm, particularly as it relates to the wandering politician. So remember, the wandering politician was the basis for applying the Metropolis algorithm to Bayes' theorem. Now what I want to do is justify that algorithm by going back to the wandering politician. And this is a Markov chain Monte Carlo. So in terms of Monte Carlo, there's a couple things involved to bring about the randomness that's implicit in Monte Carlo. One is a coin toss to determine whether the politician looks left or right. And secondly, there is this accept-reject rule that determines whether the politician stays on the current island or moves to the proposed island. So what we can now do is consider some of the probabilities that confront the politician as the politician makes the decision whether or not to stay or to move. So what we're going to do is we're going to start the politician on island number 1. So there's the politician on island number 1. So next morning they wake up, flip a coin, 50% chance of going this direction, 50% chance of going this direction. If they go in this direction, because the population here, 400 is greater than 100, they'll move. So the probability of moving to island number 4 the following day is 0.5, the coin flip, times 1, because this population is bigger than that population. The probability of moving to island 2 is 0.5 because of the coin flip, 1 because this population is greater than that population. Those are the only two possibles. It can't move to here, and because both of these are greater than this, it can't remain on the first island. So, at the end of, of the first day, 50-50 chance of being on those two islands, we'll just randomly select one. Let's say it happens that we select that the politician is on island number 2. So now the politician is on island number 2. And the politician can look to island number 1. There's a 50% chance they look in that direction. If they look in that direction because the population is smaller here than here, then the probability of moving is only 100 over 200. So the probability the next day that they would be on island number 1 is 0.25. There's a 50% chance that they look to island number 3. And if they do look to island 3, because the population here is larger than the one here, they'll move. That gives us 0.5. There's no way they can get to island number 4. What's the probability that they stay on island number 2? It's the difference between 1 and the sum of these, so it's 0.25. And so we can do that for the other islands, and what we come up with is a table that looks like this. So starting on island 1, there's the values that we saw. Starting on island number 2, there's the values, and we can do it for the other islands. And then we can convert that into a matrix. So just taking these numbers here, made them into a matrix. And this is known as a regular stochastic matrix. It's stochastic because each one of these adds to 1. And it's regular because all the values are positive. And now I want to go over some vocabulary. And the first term I want to consider is the term state vector. And if we consider the example of the wandering politician, this would be an example of a state vector because it shows the state that the politician is at any one time. So in this particular example, we're saying that the probability of the politician being on island 1 is given here. The probability of the politician being on island 2 is given here, etc. And the next term is this idea of a Markov chain. And a Markov chain is a system. It's a dynamical system, so things are going to change over time. It's going to involve state vectors at a succession of time intervals. These state vectors are going to be probability vectors. So if we look at our state vector here, it's a probability vector. All these probabilities add up to 1.0. And there's going to be a formula we're going to use to determine these state vectors at a succession of time intervals. And here's the formula right here. It has a number of components. The first component, P, is our transition matrix. There's a transition matrix. This x at k is the value of the state vector at time k. And what happens is, what we're interested in is getting the state vector at time k plus 1. And we're going to arrive at that by multiplying the transition matrix by the state vector at the previous time. So, if we think about our wandering politician, we started our wandering politician out on island number 1. So initially our state vector would look like this. There's a probability of 1.0 that the politician is on island 1, and there's a probability of 0 that the politician would be on any other island. So when we multiply our transition matrix by our state vector, we get a new state vector that shows the probability of the politician being on different islands at the next time. And so what we see is the next time there'd be a 50% chance that the politician would be on the second island and a 50% chance that the politician would be on the fourth island. And so we can continue this on. For the next iteration, P would be the same. P is going to be our transition matrix. But now what we're going to use is our initial state vector is going to be this one. So we're going to take the state vector from the previous time. We're going to multiply it by the transition matrix, and that's going to give us our new state vector. And so we can continue this over and over again for many iterations. But what happens in a simple system like this is that relatively quickly, after as few as 40 iterations, things settle down. Things settle down so that the value of state vector, I should say, at time k is equal to the value of the state vector at time k plus 1, and equilibrium has been achieved. So why this happens isn't particularly obvious to me, but Krushke provides an explanation if you're interested in that. But what's important is the relevance of this to Bayesian statistics. Because think about what would happen. What we could do is, instead of doing 14 iterations, we could run this thing for 11,000 iterations. And we could take the first 1,000 iterations, the first 1,000 time intervals, and we could throw them away, just so we'd be absolutely certain that we've reached a steady state. And then for the next 10,000 iterations, we could randomly sample from this vector, and what we would arrive at is a probability distribution of visits that would be equal to the relative population sizes of the islands. So what we're dealing with is Markov chain, Monte Carlo. And the reason it's called Markov chain is because we have this Markov chain process that I just described. In terms of it being Monte Carlo, that's because there's chance involved, there's stochasticity, and it enters in a number of places. One is, if you think about the way the wandering politician works, there's the coin flip, and then there's also this accept reject rule, such that if this ratio is less than 1, then we take a random draw from a uniform distribution going from 0 to 1, compare it with this ratio, and that determines whether or not the politician moves. So, Markov chain, Monte Carlo.